All right, so what this is about, you guys know how you know the fuel systems, like the delivery systems and the components, the fuel pump, the lines, the filter, the injectors. But on a fuel injection system, we need to precisely control the air-fuel ratio, which means we need to control the exact amount of fuel that the injectors spray. So this is less about the injectors and more about the ECM and what we call input process output. So here's what that is. Inputs, that's like sensors. So we're going to talk about a whole bunch of sensors right now. Then process is like the processor, that's the computer. And we'll look at how the computer adjusts and how it controls things. And then output is the actual outputs that do work. So an example of an input would be like a sensor. An example of an output would be like maybe a motor, or an input might be the fuel rail pressure sensor. An output might be a fuel injector, right? So one of them senses. It's kind of like if it was your body, you have senses that feel. What are your senses? You remember them? Touch, smell, sight, sound, right? So those are like sensors for your body. But you also have muscles that do work, right? Those are outputs. Okay, so this is essentially what they've made the fuel injection system do. It looks at sensors, it reacts with programming in the computer, and then it controls outputs as a result. So typically, right now, what I normally do shocks people, and I've already decided who I'm going to do it with. Yeah, Mason, good job. Okay, so what happened right there? Mason saw something. Mason visualized he saw a marker flying at his face violently. And his brain program was like, I should catch that or block it or something, which is an interesting concept as to like how your brain is programmed even from a young age to try to like not get hit by things, right? But it's programmed. And then the output was using my nerves, contract my bicep, use my deltoid, use my forearm, and block it from hitting me in the face, right? So we just did an experiment right there. You passed. You can throw it back now. Oh, ow. Okay, there's something wrong with my programming. I saw it coming, but I didn't react appropriately, right? And then where it goes from there is fuel trim is like one of the more complicated input process output parts. So we're going to really dial in on fuel trim, and I think it'll make a lot of sense. All right, so the first sensor, TPS. Anybody guess what that stands for? Throttle position sensor, yes. Now, it may have a little bit of other versions of the name, but it's basically just throttle position sensor. So you can see we've got a throttle body right here, and we've got a TPS sensor, and that's going to be really critical to the ECM because the ECM needs to know what your throttle position is. Like, for example, if you're at idle, you can expect your TPS is going to be fairly close to zero. The way it does it, we talked about this a little bit in the A6 applied to A8 electrical stuff, is the TPS sensor gets a 5 volts and a ground, and then depending on the mechanical position of like the throttle plate, right, it'll generate either a 0.5 or a 2.5 if it's 50% throttle, remember that? Or if it's a wide open throttle, it might be like a 4.5 or 4.7. So what's happening essentially is that sensor is going to generate a voltage, send it to the ECM. The ECM is going to interpret that voltage, 2.5 volts. What does this mean? And an engineer goes and programs it to say that's 50% throttle. So your ECM knows where your throttle's at. Makes sense? Through the TPS sensor. So we're going to do an overview on quite a few sensors, but part of the reason you need to know this is we have problems with the TPS sometimes. You might get a throttle position sensor code, and when you go to diagnose it, one of the things you need to do is check to see if it's getting 5 volts. Check to see if it's getting ground. If it's not getting 5 volts, then you need to see if the ECM is providing 5 volts. If it's providing 5 volts, but it's not making it to the sensor, maybe it's open in the wire. If the ECM is not providing 5 volts, maybe it's a problem inside of the ECM. And same with ground. And then with signal, we'd usually probe right here, and let's say it's 50% throttle, you're getting 2.5 volts. You should get 2.5 volts also at the ECM. If it's got 2.5 volts at the sensor, but not 2.5 volts at the at the ECM, it'd be an open in the wire. Or if it doesn't have 2.5 at the TPS and it's at 50% throttle, it sounds like more like an open in the sensor. We just have to verify the sensor gets the 5 volts in the ground that it needs, right? So the way we diagnose this, we covered a little bit more in that electrical part, but we'll kind of go more over how these sensors are inputs to the system, okay? And then TPS has evolved a bit. It was just a basic TPS sensor like I showed, but then on the newer stuff, we've gone to drive-by-wire. Anybody know what that means? All right, here you go. Here you go. Yeah, purely electrical. That's a good way to put it. Yeah, you used to, Ronnie knows, you used to slap the throttle and that would pull a cable and the cable would pull open the butterfly and the carburetor and you boop, 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 boop. But there's no mechanical connection on a modern car. You're literally pushing the pedal. The pedal has a sensor. That's the next slide. That sensor provides an input to the ECM. The ECM looks at programming and the ECM says, command the throttle motor open. The motor is an output. But the reason that we look at this as an input is because a lot of times what they do, they combine the motor and the throttle position sensor. And a lot of times it's 2 throttle position sensors in one housing for redundancies. And they put it all right here on a fully electronic throttle body. There's no mechanical connection. Now, who can guess why there'd be 2 sensors reading the same thing? True, but why we could do it with one sensor? Exactly. It's redundancies for safety, right? So remember, I told you, way back in the day, they had unintended acceleration, and I'm not really a believer that that occurred. I think that it probably occurred. I guess I should reword what I'm saying. I believe it happened, but I don't believe it was a malfunction with the computer or the sensors or the motor. I'm very firm in my belief that I think that the customers had too many floor mats and the literal pedal was getting stuck, at which point the pedal was reporting wide open and logically the motor would give you wide open and accelerate. I also tend to believe that because, these customers, if they couldn't think enough to put the car in neutral or, shut the car off or something, I just don't think they have a real good understanding enough to know to not double and triple floor mats. And so some of that's on the manufacturers for not building even more fail safes in. Like, for example, on a modern system, if you press the brake pedal, the ECM sees the brake pedal switch and that overrides the throttle. They probably should have done that. That's fair. That's a fair assessment. They've also modified the pedals to be shorter to make up for customers having stacked and things and stuff, just to eliminate the possibility of a pedal sticking. But they're kind of like, that's the problem. When you have to know less and less to operate the vehicle, the customers adapt and they literally know less and less. And then they're shocked when the pedal sticks because there's a bunch of junk down there, and then they're quick to blame the car. Makes sense? So if you look at this, 2 sensors in one and a motor, cool. And that's going to work in conjunction with the APP, accelerator pedal position, right? So that's the sensor that was not malfunctioning, in my opinion. I believe that it was reading exactly right because this is also a redundant sensor. There's 2 sensors in one. And then when you apply the gas pedal, the accelerator, if you will, both of these sensors have to be in agreement. So typically you'll have a sensor that may go from 0 volts to 5, really from a half a volt to 4.5 or so. And then you have the other sensor that'll go from about 4.5 to about 0.5. And so they should read different numbers, but those numbers should always check out against each other. Make sense? So like if you're at 10% throttle, maybe that should be 4.2 volts and 0.8 volts. And if those 2 voltage readings are accurate, the ECM sees that and it says like, yeah, that sensor's working good. Both sensors are working good. It's legitimate. But if one of them ends up off, the ECM will see that and say, APP1 and APP2 don't agree. You know what the result is? Sets codes, puts it in limp mode, the car will barely move, right? So when the customers are claiming, well, it's an electronic system, there's an electronic failure, I'm kind of thinking like, but it's a double redundant. Like, so both of them happen to fail. So like one sensor just randomly freaks out and goes to 4.5, and the other one happens to randomly just freak out and read at 0.5 in perfect harmony. And by the way, they have to change at the exact millisecond for it to be a legitimate one. If one changes to 0.5 and the other one changes just 3 milliseconds later to 4.5, that's a correlation issue that it's done. It's in limp mode, right? So you had two different mice who were linked, and they had the same DNA, and they were born, it was like, no, like, I don't think so. I don't think so. I just don't. An open would make a 0 volts. If they chewed a ground, it would make a 5 volts. That's all. This system is, in a way, this system is so sensitive, it's a pain in my butt. I'm going to be honest with you. When these sensors just wear slightly and the voltage just changes slightly, it puts it in limp mode. So a lot of times we're chasing these issues where it's putting itself into limp mode because they were so cautious about unintended acceleration. All right, cool. But you guys can kind of follow it. 2 sensors in this. And if we back up, remember, 2 sensors in this. And guess what? Really, all 4 of them have to agree, right? So these 2 have to agree with each other. These 2 have to agree with each other. And then whatever you're calling for on the accelerator pedal, if it commands the throttle to 50%, both of those sensors have to read 50%. It all has to be in agreement, or the system is in fail-safe or limp home mode. Cool. All right. We just gave you the first example of the input process output. Because there's 2 sensors that are inputs to the PCM or the ECM, right? And if you ask for 50% throttle on your APP, now we all know what APP is, right? If you ask for 50% on your APP, that's going to send 2 voltages to your ECM, and your ECM is going to say, oh, customer wants 50%. Then what it's going to do is send a signal to the actual motor, which is right here, and it's going to command motor move how much to what percentage. The APP requested 50%. What do you think the ECM is going to command on the throttle motor? It'll roughly say like 50%. Now, technically, we could go into the programming and we could say, like, when the customer wants 50%, don't give us full 50%, right? So that's the processing part. Like, let's say, Bo, you're getting picked on today. You put it in first, you punch it to the floor, and you're spinning the tires and all that type of stuff. You've got other sensors that are going to tattle on you for spinning the tires, your front wheel speed sensors.
I turned my traction control off.
All right. And so there they are spinning. And if your traction control was on, your ECM is going to say, like, yeah, he wanted 100%. We commanded 100%. It moved the throttle motor to 100%. But then the tires started spinning. So that gave a new input to the ECM. And the ECM's like, oh, never mind. Don't give us 100%. Drop it down to 20%. Now, what's that going to do? Close the throttle, and it's going to kind of fall on its face a little bit, but that's going to help regain traction, right? So this is the first example of the whole process, right? The input started with the APP. The output was move the throttle motor, right? There was some processing to say move the throttle motor. And then we had another input providing we're spinning the tires. And then the ECM is programmed to say, like, oh, chill the throttle out a little bit so we can regain traction, right? All right, what about, a thermistor? Now, there's going to be several thermistors. Thermistor we talked about just a bit in the electrical part. The thermistor is kind of opposite of everything in nature. Normal things in nature, when you heat them up, they get more resistance. Thermistors of the NTC type, when you heat them up, they get less resistance. When you cool them down, they get more resistance, but it's very predictable. So if the temperature changes, it'll change the resistance really in a nice, clean, linear fashion. So in other words, these are electrical devices that can measure temperature. It kind of sounds like a thermometer, huh? But it's a thermistor. So we're going to use a couple wires on here. It's a voltage divider. We talked just a bit about it in the A6 part, but Essentially, if this thermistor is threaded into a coolant passage, what do you think it's measuring? Bingo, ECT, engine coolant temperature. That's a very important input to the computer. For example, when you go to start the car, if your engine is cold, we want to ramp our idle up. We want to richen our air fuel mixture. We want to have a little bit more gas. Like if you go to start a lawnmower, a weed whacker or something, you got to pull this little knob. You know what it's called? Right, the choke. But you don't have to do that when you get in your car. That's because the engine coolant temperature sensor measures, oh, it's cold out, tells the ECM as an input. The ECM says, oh, yeah, my programming says when the coolant is cold, richen the fuel mixture and bump up the idle. That's what your choke lever does anyway. Makes sense? So we've eliminated the need for a choke with something like this. Cool. Now, what do you think would happen if your engine coolant temperature sensor was reading the wrong temperature and it thought it was warm when it was cold? Yeah, exactly. It'd be just like if you try to start the lawnmower with no choke. It'd be like, I'm pulling and pulling and pulling and pulling and it's struggling, right? And so it's going to be the same thing. So if you had a car that has an extended crank, it might be a good idea to go into your scan tool, go in live data, just take a look at your engine coolant temperature. The time that I would do it is when I first walk out to the car and I go to crank it and it doesn't start. I'd stop cranking it, I'd leave the key on and I'd look at my intake air temperature, my coolant temperature, and if it's even got an oil temperature, a transmission temperature. If the car's been sitting overnight, all those temperature sensors should be the same because it's all going to be at ambient. All the temperatures start off the same. Then when you start it, your coolant's going to start heating up and your oil's going to heat up and your transmission's going to heat up and your intake air might heat up a little bit. Your ambient air temperature sensors out near the bumper typically, that should stay the same, right? So the time to check them all for accuracy is when they're all at ambient temperature. They should all be within a few degrees. Cool. And if they're not, like if this one's reading 40 degrees higher than the actual temperature, you probably found the issue more than likely. Right? So, but we have other ones. Intake air temperature. And the intake air temperature is a little tiny thermistor in here, but it happens to commonly be built into the mass airflow sensor. So we're coming up with mass airflow next.
So my mass airflow sensor,
sure.
keeps going on and off, like.
I see. So it's intermittent. It passes, it fails. Remember when we did monitors? The monitors the test, right? It runs the test, it passes, light goes off. It has to probably pass several times for the light to go off, but then it fails and light comes back on. So you got intermittent. And it may very well be an intermittent connection up in the sensor like this, but is it possible that it's a connection issue right here at the actual connector with the terminals? You see, it might be in your best interest to check this connection right here and maybe even check some of your wiring. The challenge is with the intermittent, you can make all your voltage measurements and take all your measurements, and if it's working, all your tests will pass. You got to test it when it's not working to actually find what it's missing. So the way I would go about this, I'll tell you I'll tell you a couple extra unofficial tips and tricks today. If I thought it was a MAF, I've seen this before, where the MAF is failing and passing, I'll go tap on this with like the backside of the screwdriver, the plastic side. And if me tapping on it makes the car stumble and makes the light come on, I think that I'm tapping and there's like some loose connection in the circuit board in here. Whereas I might go down here and grab the wires and I might move those wires around. If that makes the light come on, then I think I might have a problem with the wire, the connector. So some of it's the wiggle test. The wiggle test. The wiggle test isn't what you do to yourself after the holiday season. The wiggle test is you grab electrical things and you wiggle them around. Tap test is when you tap on stuff. The light won't go off until your monitor runs and passes multiple times, typically, at least once. So the other thing you could do, you could look on, remember this is an input, right? So if you're looking at specifically intake air temperature, you could pull that up on a scan tool under live data, and you could read that temperature and have it say like, I don't know, maybe right now it'd be 74. And then you could tap on it, and all of a sudden that 74 drops to negative 40. You'd be like, oh, that's an open. But what you're manipulating when it drops to the negative 40 is narrowing it down. Is it in the harness? Is it in the connector here? Is it in the circuit board of the sensor, right? Because boiled down to the most simple form, customer doesn't really care how you found it. They want to know, is it a bad sensor? Is it a bad harness? Is it a bad ECU? Or is it a bad something else that's not even related? So sometimes these wiggle tests and tap tests can be more effective than hooking up a fancy oscilloscope and stuff. All right, but that was for the IAT. All that lesson is similar for all the other sensors too. Another type of thermistor, transmission fluid temperature. So we'll have a transition fluid temperature sensor inside the transmission that's immersed in the automatic transmission fluid under the pan. All these are inputs. And there's even some more rare ones, a cylinder head temperature, but a lot of times, this was common like on some GM stuff where they'd have multiple temperature sensors and they might have a couple in the heads. They'd have one in the left bank and one in the right bank just to monitor that specific part of the cooling system. But for your average typical car, there's going to be one coolant temperature sensor, not an additional cylinder head temperature. And engine oil temperature, all these sensors look kind of the same. Yep. So, and there's an engine oil pressure, which is coming up next, but this is oil temperature. So we've got oil temperature, coolant temperature, transmission temperatures, coolant temperature. Did I say that? Intake air temperature. There's all these temperature sensors. You want to know the really cool thing? You diagnose them the same. All the temperature sensors are the same. And that part we covered a little bit in the electrical part, but it's going to be, the most simple way is going to be measuring the resistance of this sensor at a specific temperature and checking it on a graph. So if it says at 68 degrees, this temperature sensor should be 10,000 ohms, you're going to literally just use the meter to measure, is it 10,000 ohms at 68 degrees? Yes or no? And if it's not, then that'd be a fail. Make sense? If you did have more of an issue in the circuit, remember, the ECM is going to provide a 5-volt reference that's going to go through a fixed resistor, then to this variable resistor. So it's all about how much voltage is between the first fixed and the variable resistor, and that'll tell you really what's going on, right? So it's electrical troubleshooting at that point. Before I go with the meter and the diagram and doing the voltage divider diagnosis, I probably use the scan tool. Remember, the scan tool is the main workhorse of diagnosis. How could you check any of these sensors quickly? And what would you look for? You could, so yeah, exactly. If you were to go under live or data stream or whatever it's going to be called, and you can look at the temperature, and then you can verify if that temperature is accurate. The way I like to do it's when it's ambient, if it's been sitting. But even if the car came in and I'm looking at coolant temperature, I can use an infrared temp gun and measure the coolant temperature and then be like, what's the scan tool say? Are they the same? Right? It's not even really that complicated. But you got to have a couple tools to do it. All right, next type of sensors, pressure sensors, which I may call transducers as well, because pressure sensor and transducers, just the same, different words for the same thing. They don't measure temperature, they measure what? Pressure, like PSI. Make sense? So thermistors took degrees and made it into volts. This takes PSI and makes it into volts. Computer can't speak PSI. Computers can't speak temperature. Computers speak volts. So we have to have devices that convert things into volts, measurements into volts. Make sense? So this is going to measure your pressure, create it into a voltage signal, and those wires are going to send it back to the ECM. All day long, that's what it's going to do. Cool. So what fluid or air? I don't know. Depends on what type it is. And just FYI, the way that we diagnose these, it's really similar to the temperature sensor. If it's the same. It's a voltage divider circuit. You can check to see if the sensor is getting voltage and ground. But additionally, let's say it was an oil pressure temperature sensor. If your temperature sensor on the scan tool reads 40 psi at idle, you'd shut it off, take the temperature sensor out, thread in a gauge, and what should the gauge read? 40 psi at idle. The gauge will check the accuracy of the sensor. Makes sense? Assuming the gauge is accurate. Cool. So the diagnosis is kind of similar. What about, for example, a fuel rail pressure? Why do you think the ECM would really want to know about your fuel rail pressure?
It has one of those like variable fuel pump functions.
True. Yeah. Maybe it has a fuel pump that's variable, that's going to change your fuel pressure depending on your engine load. Absolutely. Even if it doesn't, even if it's just got a fixed fuel pump, that your fuel pressure can vary depending on how much your injectors are open. The more fuel you're spraying, typically your pressure is going to drop because you have a lot of, it's almost like a leak, right? You have a lot of fuel spraying. Like if you have all the faucets on at your house, you notice they tend to drop in pressure. And you can just tell if it's only one or all the hoses outside. But if you have like a bunch of stuff running, you turn the hose on, it's kind of like a lot less, right? Same thing. We want to know what the fuel rail pressure is, especially when we get into how much fuel are we going to spray. If our fuel rail pressure is high, we need to open the injectors a little less. If our fuel rail pressure is low, we need to compensate and open our injectors more because the pressure is a little lower, which means the volume is going to be a little less. So we need to make up for that with time. Make sense? So that's kind of the direction we're going. And the cool thing is with some of these pressure sensors, actually, they can be a 3-wire as well. So this pressure sensor would be a 5-volt reference. Maybe that's the red one. It would be a ground, and then it would generate a signal based on kind of like a position sensor based on the position of that diaphragm inside. Cool. So that would be a little bit more similar to diagnosing a position sensor like we talked about, like the TPS. Cool. Here's one, engine oil pressure. It's common. Oil pressure is not going to be an input to how much fuel we spray. Oil pressure sensor is most likely going to be input to 2 things. One, your instrument panel. If your oil pressure is low, why do you think the instrument panel should know? Yeah, and like if it's a car with a gauge, your oil pressure gauge is going to read low, and you're gonna be like, "Uh-oh, something wrong." Or if it's a car with a dummy light, an idiot light, what's it going to do? It's going to light up a light, and it looks like a lamp, and you'd be like, "Oh, it's the genie lamp! I get to pick a new car! Woo! I won!" Yeah, that's because if that oil pressure sensor is reading 0, you probably have 0 oil pressure. You're messing some stuff up. But the pressure sensor itself could fail. So again, we could diagnose this by looking at the scan tool, seeing the oil temperature, the oil pressure reading, and then comparing it to a gauge. And if the pressure reading and the gauge are the same, then it's legit. And if it's 0, that's not good.
How do you tell without running the engine?
You have to run the engine. So that's the thing. Honestly, if I got one that came in with the red oil light, the first thing I'm checking, right? Does it have any oil? Yeah. So if you're running it with no oil, that's kind of incompetent, right? So you can't be running that thing with no oil. So check the oil. If the oil's there, it's like, hey, what are you going to do? The customer brought it in. You got to run it to diagnose it, but you got to do what you got to do,
I was young, my father-in-law supposed to be changing oil on a gear geo prison.
Oh yeah, I remember this.
Yeah, he was supposed to change the oil, and the oil that was already on, and I had warned him about it.
Yeah.
He said, no, it's okay. Drive it. I'll change it when you get back from work.
Oh.
As soon as I started pulling off the freeway, or pop, smoke.
Oh yeah. Blew it up. Blew it up. Yeah. So you guys just understand, if the red oil light's on, it's not to remind you to change the oil. That means your oil pressure is low. It knows because that's this sensor's job right here. That's what this sensor's whole job is. So it doesn't change how much fuel, it warns the driver. Now, some vehicles, not really a lot, but like more with some diesels or small engine stuff, if this oil pressure sensor reads 0, it'll actually shut the engine off to protect itself. That would have been kind of nice. The problem is, imagine your GeoPrism is programmed this way, and the logic of the ECM to say, oh, if the oil pressure is 0, like kill the fuel pump and kill the injectors and kill the ignition, so it just dies. What if it died on the freeway and you got rear-ended? Your family would be suing the heck out of GM/Toyota back in the day. So like it would save the car, but maybe at the expense of the person's safety. The person's safety always wins in your typical consumer vehicle. Not necessarily true in like a heavy duty application. Like if it's some diesel machine to move things around a yard, they'll be like, oh no, that's not on the freeway. If the oil pressure's low, shut that sucker down so we can go out there and fix it before they blow it up, So it does vary. That's all in the programming. Cool. Both of those are good options. Now, another one here, map. So we talked a little bit about a map, and I know that some people were kind of like, what the heck is a map, MAF, or whatever? The map sensor is manifold absolute pressure. This is going to measure literally how much pressure is in your intake. All right, let's go back in time. Do you remember when we were doing vacuum tests, like way back in the beginning? We did engine vacuum tests. That's what this does. This measures the amount of intake manifold vacuum, but it does it electrically. So it's going to take that pressure, convert it into a voltage, and then it's going to generate typically on the middle wire, right? It gets 5 volts, it gets ground, and then on the middle wire, it's going to generate between a 0.5 volt and a 4.5 typically. That's going to be an indication of how much manifold pressure there is. Cool. So again, your ECM doesn't read a gauge, doesn't read inches of mercury or PSI. It reads volts. That all this really is, it's an electronic pressure sensor. That's it. And we poured it into the intake. Now, typically, that's a major input to how much fuel we need to spray. If you think about, if you're at closed throttle at idle, your throttle's closed, your engine's going to make a lot of vacuum. If you're at closed throttle, you think you need a lot of gas or a little gas? Closed throttle. Not much, right? But what happens if you step on it? Mo gas, right? When you step on it, this goes from 21 inches of mercury to 0 inches, and it's going to be like, whoa, we're under wide open throttle. Spray those injectors, spray a lot of fuel, right? So this is a major input on how much fuel to spray. Cool. But the thing is, it has to be calibrated because the manifold pressure is going to be relative to the barometric pressure outside, right? So if you're, let's say, Huntington Beach, do you know what the elevation is in Huntington Beach? Like 0. Yeah, exactly. Like maybe 3. Like, all right, 0 is slightly an exaggeration, right? So, but what if you left Huntington Beach and you went to Big Bear? 6,500, 7,000, in some of the highest spots. Your manifold absolute pressure is going to change, and your barometric pressure is going to change because of your altitude. So we don't just need a map sensor, we need a barometric so that we can compare it to the map. So that way we know, like, is our pressure lower because we're in Big Bear, or is our pressure lower because we're stepping on the gas pedal? So this helps us to determine why our pressure is what it is, right? So the baro and the map, sometimes the map and the baro are one sensor. Other times they can be separate. Another sensor that's actually not included because it's really the same as a map is a boost pressure sensor. Why do we have a boost pressure sensor? What boost? How'd you get the boost? Most cars don't have boost. What type of cars have boost? Supercharged, turbocharged cars. So if you have a car that's forced induction, that's actually going to get positive pressure when the supercharger gets spun up by the belt, or when the turbocharger spools through the exhaust gas. So you're going to have a map sensor that'll read not only negative in inches of mercury, it's also going to read positive in PSI of boost pressure. Sometimes they even have them separate. They'll have a map for the negative and they'll have a boost for the positive. But like a lot of times they'll have a map sensor that can read both, right? That's another critical input. If you're under boost on the on a supercharger or turbocharger, you need not a lot of gas, you need a lot of gas. Makes sense? So these are major inputs to the ECM to know how much fuel to spray. Cool. Here's another one that we've discussed just a little bit because this is actually part of ignition more so than fuel. But the knock sensor bolted on the block somewhere, sometimes in the head, and it's a microphone, and it's literally just going to monitor knock. Remember, so when we talked a little bit about like if the ignition timing is too advanced or if the compression is too high, it'll start to pre-ignite, and the knock sensor will detect that, and the knock sensor will be like, hey, you need to retard the ignition timing to protect the engine. Cool. This is another input to the system because now we're mostly focused on input, process, output. All right, but less for fuel, but it still could be for fuel too. And these are interesting, FYI, 2-wire. A lot of times we'll send a reference voltage, and this sensor will modify the reference voltage based on, get this, the vibration of a piezoelectric crystal. And so like it's literally a crystal, and the crystal, depending on the pressure on the crystal, it'll generate a voltage or modify the voltage. So when it's knocking, that's going to actually put pressure on the crystal, and the crystal will essentially feel the vibrations of a knock and generate a voltage. And the ECM will be like, oh, that's like a legitimate knock. Like you could go on the original knock sensors, they were kind of janky. You could like start tapping on the engine and the engine will start running weird because the ECM's like, oh my gosh, it's knocking. And there was even people driving over rough roads hitting like gravel, and the car would lose a bunch of power. And it was normal because the ECM couldn't determine what an engine knock was versus like what a clunky rattle is on gravel. And so they've reworked the ECM's programming to be like if it's not in the same frequency of engine rotation, we know it's some external knock. But if it's on the same frequency of, let's say, cylinder number one, it'll be like, oh no, that's my engine knocking. Now let's retard the timing and let's pull power from there. Makes sense? So they've gotten a lot better, but they used to be kind of ridiculous. Like back in the day, if a tech ever left one of those loose, that car would run so bad because that sensor would be rattling around and it would seem like it was engine knock. So they're a little better now. Okay, and then the MAF with an F is mass airflow. This sensor is a little different than the others. If it's a mass airflow, what do you think it reads? Air what? Flow by volume. It's the mass of the air flowing. So literally it tries to, or by weight, not by volume. It's trying to measure the weight of the air flowing past the sensor, okay? So, which is not a super critical ordeal, but like if you were to pull up live data, a lot of times say G/S is like grams per second, not gallons, grams. It's measuring in weight. Part of the reason this one's so critical is, you guys remember we talked about the ideal fuel ratio, air fuel ratio? 14.7. 14.7 parts of air to 1 part of fuel by weight, not by volume. So if it measures 14.7 grams per second, it should spray 1 gram of fuel per second to have the exact ratio. Yeah? You like it? And so the mass airflow sensor is another major input on that. Some cars don't have mass airflow, but most of the newer cars all have a mass airflow sensor, and that's going to measure all the air that comes in as long as it's not sneaking in. Makes sense? So in a little bit, we're going to talk about air that's sneaking in there is unmetered air. And the problem is the ECM can't account for that because it doesn't know that it's there, and it's going to mess up our fuel trims. That's coming up. All right, so if you look at this, it's going to be in the intake ducting. So here's your air filter. All your air is going to get pulled in here. and it's going to all go through the MAF. It should all go through the MAF, and there's different types of MAF, but all the MAFs, their goal is to measure the quantity of air that is entering the engine. Okay, pretty simple. Now, just as a preview, what if we had a little leak right here? If you notice, the MAF is over here, so the air comes in from the right. The sensor measures it, it counts it. It's like let's say you're gonna have a pizza party, pizza and soda, and so everybody who comes through the door, you're like, yep, I'll take the $5, and you put the $5 towards a little more pizza and a little bit more soda. And if you get 10 people that come through, you should have the correct amount of pizza and soda, right? But what if some people are sneaking in the side door over here? They pop the window open, they're jumping in the window, and they're eating pizza and soda. Do you have enough for them? You didn't collect for that, right? This is the admissions gate. And when you're passing through, this mass airflow sensor is reading that. Then unfortunately over here, you got a crack, and these are the people sneaking in the window. You didn't collect any money from them. You don't have enough pizza and soda for them. In other words, you didn't measure this air, so therefore you're not probably going to have sprayed enough fuel to compensate for that extra air. Makes sense? Now, there is a way that we'll trim that. We'll correct it. But so you understand in a little bit, when we talk about unmetered air, that's basically unmetered. That's air that we didn't collect for. Make sense? All right, cool. There's different types. The most common is going to be this hot wire type MAF. So this is going to use a little hot wire. And what that means is it's going to send a certain amount of milliamps or amps through that wire to maintain a specific temperature. So I don't recall the temperature, but it's hot, hundreds of degrees. Let's call it at, let's go with 300. Don't fact check me on that, because I'm telling you, I don't actually remember the temperature. It might actually be hotter, but let's go with 300. The more air you get, what do you think is going to happen to that 300-degree wire? It's going to cool it down. So do you know what the MAF does? It sends more amps or milliamps to maintain 300. So the more air that flows, the more it has to send electricity through the wire to maintain 300. The mass airflow sensor is going to look at how many amps had to flow through that wire to maintain 300, and that's going to be proportional to the quantity of air that's flown in. It's kind of interesting, right? So that's a hot wire. Why does this matter to you? Well, I'll tell you. You got a dirty air filter. Customer got a dirty air filter. You want to help them out. So what do? You can pop the air filter out, and you're going to blow all the dust and the junk out of it. Well, that sounded nice, because I mean, that dust and junk can contaminate this hot wire on the MAF. But a lot of times when you blow the stuff out of the air filter, you kind of unravel some of that cotton packing. And then next thing you know, a little piece of cotton breaks off and it goes flying by and it hits this 300-degree hot wire. And then it like burns onto it and it kind of covers it. And another one. And next thing you know, the mass airflow sensor is essentially wearing a blanket. And so if the mass airflow sensor is wearing a blanket, it doesn't feel that cold anymore, right? So you'll have a bunch of air flowing through and the MAF is like, I don't feel no air. And it'll get a false reading. It'll be like, yeah, we're flowing 12 gallons per second when you're really flowing 25 grams per second, right? So it's like, this sensor, like any sensor, can be inaccurate. I like the temperature sensors and the pressure sensors because we can put a gauge on and see if they're accurate. We can measure the thermometer and see if they're accurate. With a MAF, it's tougher. It's like, it's reading 12 grams per second, but is it 12? Is it 6? Or is it 24? I don't know. It's a little tough. So the way to diagnose these gets much more complicated. Have you guys seen mass airflow sensor cleaner?
Yeah.
It's not a bad baseline. Clean the MAF, especially if it's got an air filter that looks dirty or messed up, or you suspect somebody might have take compressed air and blown it all off. It wouldn't be a bad idea to start with mass airflow sensor cleaner, but yeah, literally. But they're just a little trickier to diagnose. So when I show you how to diagnose these in a little bit, I think I think you'll understand partially why this is one of the more complex courses. Like brakes and suspension, and even to an extent manual transmissions and stuff. It's not even electrical is like you measure and it's good or bad. This gets tough. You can't really measure the grams of air per second, so it's a little tricky. All right. But then they also have vane type. So they actually have mass airflow sensors that would physically, air would move a door, and depending on how swung open the door was, it would change a voltage, and that voltage would indicate how much air is flowing through. So there's anything from the hot wire to the vane, which was the opening of a door mechanically. These are old school. You won't really see these anymore. A Karman vortex, which really measures through light how should I say, like it's like how disturbed the air is. So like if you have just a little bit of air, it won't really disturb the air. But if you have a lot of air, it actually creates this vortex, and this LED and a mirror can measure the vortex, and that can make sure that can effectively determine how much air is flowing. It's kind of weird. This one is also prone to different types of failures. Mirrors and stuff, for example, they don't like to get dirt on them, right? Then it's the image wouldn't be that clear when we're looking for those vortex. The good news for you guys is when we look at these three, like we're generally testing these in the same way. We're trying to look at the reading and see if it correlates with the airflow. So like, for example, you jump in the car, you don't even crank the engine, you just turn the key on. What should all your mass airflow sensors read? Yeah, because you're not flowing any air. Then you should start it, and you should get somewhat of an accurate baseline, like all the, what do we got out there? Nissan Sentras at idle should read kind of similar. Make sense? So you a lot of times can get like a known good reading. If it's reading way off right from the get-go, you know it's messed up. Then at certain amount of RPM, it gets a little harder because you have different load and things on the engine. But at certain RPM, you should get roughly a specific number. So we're diagnosing them a lot through the scan tool. And it doesn't really matter which type it is, right? So we're still looking at a number and seeing if it follows like known good numbers. Cool. If you get into something like this, we don't really go in there and do anything with the photocoupler, the mirror, things like that. It's like if you determine that the number is not what you expected, and it seems like the mass airflow sensor is the reason that the voltage reading or the gallons, the grams per second is off, then you're probably going to sell a mass airflow sensor. You're not going to take it apart and do that much. Like we don't. You can for the hot wire. You could. These are fairly easy to pop out, and you can visually inspect the hot wire. That's not a bad idea. But with these, there's not a whole lot you do. Cool. What about switches? What do you think a switch would provide? Yeah, so like a switch can tell you if something's on or off, or let's just say we put a switch on the, you could even do it on the throttle. If you go to wide open throttle, you make it close a switch that indicates wide open, right? So you could put a switch. How about on the brake pedal? You think the ECM might want to know if you're stepping on the brakes? Yes, put a switch on the brake pedal. When you step on the brake pedal, it'll close the switch. Oh yeah, they do. That's how they, not only they turn the lights on like the brake lights on, they'll cancel your cruise control. A lot of times that's an input to the whole powertrain control system too. So a switch could be a number of things. For example, if it's the brake pedal switch, that's an input to the computer for what the brake pedal status is. However, you could also have a switch that's there for like different drive modes. Maybe you have a car that's pretty new and got some cool things and you want to put it in sport mode. You pressing the switch in sport mode is an input to the ECM to say, hey, let's make the exhaust a little louder. Let's advance the timing. Let's spray a little more fuel. Let's make it race car because they just put it in sport mode, right? So switches can do a number of different things. Indicate the position of something or act as an input that the customer can select. Cool. Like another example of a switch, we have an inertia switch. Remember we talked about that in the part one? In some of those old Fords, like if you got rear-ended, they knew that you could have ruptured a fuel line or damaged the gas tank. So the inertia switch will sense the impact, bam, and it'll open the switch, and the switch will basically mean that the fuel pump relay doesn't get voltage or ground. It'll make sure that the fuel pump doesn't come on. So that way, if there is a leak, it's not spraying fuel all over the scene of an accident. That'd be kind of scary, right? So there's another example of a switch. Or even like, oh, here's a good one, a level switch. So if you were to have an oil pan with a level switch in it, once your oil level is below this level, the switch will connect and it'll make maybe not your Genie low oil pressure light come on, but you may have a low oil level light. So it's cool when you have a pressure sensor and a level switch. If it's low oil pressure, it'll say oil pressure low. But if it's low oil level and the switch detects it, it'll just say your oil level's low, add a quart or two or whatever you need to add. Cool. So switches can do a lot of things, but one thing about a switch is it's just on or off. There's no like your oil's a little low. It's just your oil's low or it's not low. Your brake pedal is on or it's off. This would be in the pan. Yeah. Your brake pedal is on or off. It doesn't tell how hard you're pressing on the brake pedal. If you want to know how hard you're pressing on the brake pedal, you need either a position switch to measure how far it is to the floor, or B, a pressure switch that's in the brake hydraulic system. The harder you press, the higher the PSI. A brake fluid pressure sensor could provide more input than just an on-off brake light switch type of thing. But switches are still valuable. For example, like a power steering pressure switch. You guys ever notice if you jump in your car and you start turning, the power steering pump can put a little load on the engine? Well, you ever notice if you turn all the way to one side, a lot of times it'll make kind of like loud noises. That puts a ton of load on your engine. We'll put a power steering pressure switch in the line. When the pressure comes up, that switch will close. It'll send a signal to the ECM, and the ECM will know, hey, bump up the idle. If that pressure switch is disconnected, you'd be surprised. You'll go to turn the car and sometimes it'll stall it, or the RPM will be so low it'll be hard to turn. It could just be a power steering pressure switch. That's another input too. Okay, cool. Oh, and of course we got speed sensors. So like I said, lots of inputs. We need all these sensors so that the ECM can make good decisions. Speed sensors in general monitor the speed or the what? Speed and position. All right, so like when I say crankshaft position sensor, I also mean it's checking the speed. If I were to say wheel speed sensor, new wheel speed sensors also check the position, right? So it's the same sensor. It all depends typically on the teeth that they read. So like you can see this is an actual sensor and it's reading these teeth on this reluctor wheel, tone wheel, they'll have different names. It'll read tooth, no tooth, tooth, no tooth. Make sense? But what we can do with these that's kind of interesting is we'll make it so that you'll have like a double gap or a double tooth or sometimes both. So if it says tooth, no tooth, tooth, no tooth, double tooth, now we know where it's at. So in crankshaft, for example, if we're using a crankshaft position and you want to know where TDC cylinder number 1 is, remember top dead center cylinder number 1, we'll maybe have top dead center be like a double tooth and then a double gap. And we'll be like, when you see the double tooth, that's TDC cylinder number 1. Now the ECM can know exactly when to fire the coil to make the spark. Make sense? So it's a speed sensor, but it's also a position sensor if it's set up to be a position sensor. And they commonly are. Cool. So there's your example of the crankshaft position. Indicates where the crankshaft is, but it also knows the speed of the crankshaft. It's mostly going to help the PCM or ECM with relation to ignition. However, if you go to crank the vehicle and you don't have an input from the crankshaft position, a lot of times it won't spray the injectors either, right? So this was mostly the fuel injection system, but it's also somewhat inclusive of the ignition system as well. This is a major input for your ignition timing. In fact, this is essentially the input for your ignition timing. It needs to know exactly where this is. They can be located in a lot of spots though. A lot of times they're like up near the crankshaft pulley. Sometimes they're in the back near the flex plate or the flywheel. Other times they're in the middle of the oil pan. They can be anywhere where it can pick up a spinning wheel with teeth on it that's bolted to the crankshaft. Sometimes they're hard to get to, just for reference. On my Hummer, mine's under the starter. You have to take the starter out to get to mine. Excellent. And then a camshaft. So this camshaft position sensor, you diagnose the same as a crankshaft. The crankshaft measures the crankshaft. The camshaft measures the camshaft. You can see this camshaft is in the vicinity of a reluctor that's attached to the cam. So as the cam spins, these little teeth and this solid part and that missing low spot, low spot, high spot, that's all going to go past this sensor. When it does, look at the waveform that it makes. Tooth, 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 tooth. And then there's like this thing, that's going to be that double gap, right? That's going to be a double. Or in this case, this is really supposed to be the crankshaft. Maybe the camshaft has less teeth, right? So however many teeth are on the reluctor wheel, that's going to determine what that waveform looks like. Now, good question for you. How did we obtain these waveforms? Do you know what tool got us those? Bingo. So if you really want to know what's up with these position sensors, you're really going to need to oscilloscope those. And then you get a full waveform and you can actually really get a full picture of it. So I'll give you an example. If you had a bad cam position sensor, you'd probably have a flat line down here where the cam is. If you had a bad crankshaft position sensor, you probably have a flat line up here where the crank is. But what if you had one damaged tooth? What if you had a damaged tooth on that reluctor wheel? That'd be hard to diagnose. You could take the engine all apart and check the teeth, or you could oscilloscope it, probe it, do a waveform, and then you might find one of these teeth that's just like hacked off, right? Damage on the tooth would actually show up as damage on the waveform tooth too. So it would have to, right? Exactly. So doing the waveform can actually give you like a really good 3D image. Like this is going to be a little embarrassing, but I'm going to tell it to you anyway. When I was brand new, I just helped a kid fix his car last night, student, and he was like, I did brakes on the car and ever since it vibrates. And I was sort of like, okay, that's weird. Yeah. And the line tech said, did you lube the brakes? And I was sort of like, you got a vibration and you're worried about whether you lube the guide pins or not. Like that doesn't cause a vibration. What else happened on the job? And he was kind of like, well, it was a Honda. So when we went to take the Phillips screw out, it broke off. So I put another screw in and I said, did it fit right or not? He's like, well, it wasn't flush. It kind of comes out. I'm like, dude, pull the car in here and pull the wheel off. And you look at it, the screw had a rounded head on it and the wheel was not sitting flat. So I'm like, yeah, that's going to vibrate, right? It sounds stupid, but to be honest, like I was not in a much better position when I started. I promise you, I'm not the smartest guy in this room. I'm not, but I put in a lot of work and effort. So one of the jobs that I had in the dealer was doing recalls for wheel speed sensors, but actually it pretty much works the same as this. They had a recall where the wheel speed sensor malfunctioned. It would show 0 miles an hour when it was really like 5, and it would activate the ABS and the vehicle wouldn't stop, and people were rear-ending, the car in front of them a lot. So what we would do is you'd bring it in, take the sensors out, and then you'd have to clean up all the rust where the sensor mounts. Because if you have rust built up, it's going to lift the sensor away. And this reading right here is going to become very faint. It's distant. All the teeth are going to be like towards the center. Like the highs won't be that high and the lows won't be that low. And it'll look like a lower speed. And sometimes it'll drop out, right? And then we'd replace the sensor. But the big job was cleaning the rust. And so cleaning the rust was detailed. I'd file, clean it up. They'd actually have us degrease it and spray it with like a high zinc primer and then let that dry and then grease it up and put it in. It was a really nice fix. It was a good recall. I got tired of filing. So you know what I used? Yeah, drill bit. A drill bit. And I did. So I chuck it up in the drill and I just be like, wee, wee. And I'm like, look how fast I am. I'm good. All right. Well, one time I kind of knew what happened, but I was like, maybe it didn't happen. Well, I kind of pulled the drill bit in a little bit. I felt it hit something. It was like, it'd be all right. Primed it, all this stuff, shipped it. My mentor drove the truck. He hits the brakes. He's like, hey, something went wrong. This thing's like wheels, it's activating ABS. And I was kind of like, I don't know. And he's like, all right, well, we'll get another wheel speed sensor, puts it in there, it doesn't fix it. And he's like, did anything go wrong? And I was kind of like, I don't know. Like, I kept thinking, like, I don't think so. But I kind of knew. Yeah, I kind of knew that I screwed it up. But like, I figured, whatever, like, it's better if I don't tell him, right? And so he ended up spending like several hours on this, goofing around and checking wires and whatever. And then he finally went and got the oscilloscope and he pulled up a waveform. And do you know what he saw? Literally, there's all these teeth, and then one of them looks like a drill bit went into it. And he's like, did you use a drill bit? And I was like, oh, yeah. And he's like, you moron, why didn't you just tell me that? Like, you're going to make me work so hard to diagnose what's wrong with this. And you knew you had a drill bit in there and you sent it in too far. And I was kind of like, I didn't think it messed it up. And it was just ridiculous. I'm just letting you know, the oscilloscope will find all your deep and dirty secrets if you do something. All right. So if the car's weird and you can't figure what's up and you checked everything mechanically and then you want to know what's up with the teeth, you oscilloscope it and you're going to find out. You find something. He found out and he asked me exact words. Did you use a drill bit? Like, I can't lie about that. I was thinking like I might not necessarily tell him I used it. If he didn't ask and I didn't tell him, come to find out later, that's kind of similar. It's like I'm withholding information on purpose. Like, that's effectively lying. I should have just told him. But now we're still good, but definitely learned some stuff on that one. Cool. So speed sensors, that's what they look like. Vehicle speed, for example. You know what a vehicle speed sensor is? It measures your, vehicle speed. So like miles per hour right there. We have a sensor for miles per hour. Why do you think that's important? Speedometer, yes, but your computer needs to know what your speedometer is too. Like if you have a car that's limited to 112 miles an hour, for example, a 94 Z28 Camaro, you get to 112, I think it was 112. And it'd just be like, bam, 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 bam. That was it. That was it. It did fuel cut. It would cut the injectors at 112 and you're done. And you're like, oh man. So it's in the computer programming to turn off the injectors at 112 to limit your speed. Why do you think?
Because if you go too fast, you might blow up cheaper tires.
Correct. I had a car that didn't have Z-rated tires. So what I did, logically, I put Z-rated tires on there. I bought a tuner. I eliminated the 112 cutoff. And really what happened on that was I raced my friend in a Trailblazer SS, and I was like getting him. I thought I had him. And then at 112, brick wall. And he's like, and I was like, never again. I can't lose again. So I had to do the Z-rated tires and do the programming, right? So again, your ECM needs to know things like vehicle speed to make sure that it can turn off your injector so you lose. But at least it kept you safe because from the factory, it wasn't rated for over 112. This, of course, all happened on a closed course with a professional driver. And no one was injured in the process.
In Mexico, as a 3D rendered by AI.
Yes, it was a theoretical. It's a cartoon-based. What's the drifting cartoon? Yeah, what was it called? Yeah, that's what happened. They did it. Wasn't me. All right, and these can look a little different because this is an AC waveform. You'll actually have slightly different designs on the waveforms, but similar. Okay, another fun sensor. What the heck does that say? O2, oxygen, yeah. Okay, what do you think an O2 sensor measures? Just oxygen, that's it. That's it. Only oxygen, make sure you understand. It doesn't measure your fuel. It doesn't measure anything except for oxygen. That's it. However, because it measures your oxygen, it can determine your air-fuel ratio. Okay, cool. But like if for some reason you had an injector that was stuck wide open and there was literally fuel dripping out of the tailpipe, the O2 sensor might not detect all that fuel. It doesn't look for that. It looks for a quantity of oxygen in the exhaust gas. Okay, so we'll come up to that. Why does it do it? It's trying to obtain stoichiometric fuel mixture, 14.7 to 1. All right, but it doesn't work until it's up to operating temperature, typically about 600 degrees. So if you had an old school car, add a 1-wire oxygen sensor, and it would send a voltage, for example, 0.1 if it was lean, 0.9 if it was rich, and if it was in the middle, it'd be about a 0.45, and that was it. But that sensor wouldn't work until it was 600 degrees. So for your first 10 minutes of driving, the O2 sensor was totally worthless. So come like about 96 or maybe a little newer, or maybe a little bit sooner, they started putting heated O2 sensors in there. So when you see O2, it's probably actually HO2S because it's a heated O2 sensor. We add a heater into there. That's what 2 of these wires are. So it'll heat up so we can actually start getting information sooner. If it's too cold, you can't trust the information. It's not relevant, right? And they're going to have it typically mounted. There's going to be multiple, like we talked about a little bit, but they're going to have that mounted up in the manifold. And again, it's going to get the greatest amount of exposure to the exhaust fumes without contamination. And it's going to look at how much oxygen is left over. If you have too much air and not enough fuel, there will be oxygen left over. That would read like a 0.2, a 0.1, a low voltage. If you had too much fuel and not enough air, that is what we call rich. There's going to be a shortage of oxygen, and that's going to be like a 0.8 or a 0.9, right? So these simply have a reaction inside, and they generate a voltage on the signal, and it's going to just provide feedback to the ECM. Okay, that's its job. That's it. And you could get into like such detail as to exactly how these work. Zirconium dioxide metal bent into a bowl shape, placed in the engine side of the sensor, which is going to allow outside air into the center that surrounds the inside of the metal, and the exhaust gas surrounds the outside of the metal, and it senses faults. Like, okay, exactly how it works, to be really honest, I don't know that well. I just don't. What I do know is if it's running lean, that means there's too much air, not enough fuel, it reads low. If it's running rich, too much gas, not enough air, it reads high. I can interrogate this sensor in several ways. So see right here, it can sense a fault like a vacuum leak. Well, how about I initiate a vacuum leak by pulling a hose off? And I look on my scan tool, what should I see on that O2 sensor reading? I pull a hose off, and it's going to suck in extra air, which is lean, which is low, right? So I don't exactly know all what's happening, because that could vary from a Denso sensor to a Delphi sensor to a Bosch sensor, right? They all use slightly different technologies. What I do know is if I think there's an issue with the O2 sensor, I'll make it run lean by pulling a hose. It should go low volts. I could also plug the hose back in, and I can inject propane. And propane is like adding a fuel, and that should go high. That should show rich. And I can just see if the sensor follows what I'm manipulating on the engine side of things. That'll give me a lot of information right there.
Sometimes they fail at like only when you start to run rich, right?
They can fail a lot of different ways. A lot of the times they'll do what's either skewed, and skewed means they'll read like closer to lean all the time, or they'll fail closer to rich all the time. They can fail both ways. A lot of times due to contamination. For example, if you use a silicone-based engine sealant and it gets into the exhaust, that'll contaminate the zirconia element in the sensor. But they can also fail, like they get kind of coated inside, and then they don't switch back and forth as quickly. So understand, because we're constantly going after the 14.7 number, typically we run it a little too rich, and then the O2 sensor shows high volts and it's rich, and then it'll be like, no, lean it out, spray less, not say less, but spray less, kind of similar. And then it'll be like, oh wait, it's too lean, richen it up, lean it out, richen it up, lean it out. But if the O2 sensor isn't going back and forth fast enough, it's kind of lazy. It's insufficient cross counts. That's a different type of failure. Both of all those are failures. Probably the most common though is actually just the heating element right here. The heating element itself actually goes bad, and you get an O2 sensor heater circuit fault. That's a heater. That's it. You don't have to check rich or lean. You just literally check the resistance of the heating element or check the voltage going in and make sure it's getting voltage. And if the heater circuit's still set, it's the heater. So it's heater circuits, very common and an easy diagnosis. An actual O2 sensor that's not reading correctly, a little harder to diagnose, may or may not set a code too. So this is similar to the MAF where you can't just check voltage readings. You have to kind of like check it with some known goods and maybe make a little vacuum leak, make a little rich, see if it follows pretty quickly. Cool. And FYI, O2 sensors are mostly replaced by what we'll call a wideband O2, wideband heated O2 sensor, or an air fuel ratio sensor. So I'm gonna tell you the positives and the negatives. O2 sensors were fairly inexpensive. O2 sensors are still used today to monitor the catalytic converter. Your catalytic converter, if you recall, when you have excess air, the cat should absorb it. When you have insufficient air, the cat should release it. And the rear reading of the O2 sensor should be pretty smooth. It shouldn't be way up and down. Cool? All right, good. Pause on that. Like I was saying, when we're trying to get the 14.7, we go a little too rich, we go a little too lean, we go a little too rich, we go a little too lean. That's good. That's way better than a carbureted car. Like at least we're on average 14.7. But on a new car where we're trying to hit the ever evasive latest and greatest fuel economy and emission standards imposed by, EPA, California Air Resource Board, these types of places, we're like, you know what? That rich lean's not good enough. Upgrade it to a much more expensive wideband O2 or air fuel ratio sensor. Same thing, different names. Domestics like the term wideband O2. Aftermarkets like the term wideband O2. Japanese like the term, and actually Japanese, European, and Asian just in general, air fuel ratio sensor. So here's the deal. If it's an O2 sensor, I'm gonna stand right on the line right here. All right, half and half. Let's make, I don't know, which makes sense. You want rich here or rich here? What you want? Rich here, lean here?
Yeah.
All right, cool. The O2 sensor can see it's rich, it's lean. It's rich. How rich is it? I don't know. I just know that it's rich. How far should we pull it back? I don't know. All the way. It's like, oh, it's lean now. How lean? I'm not sure. I just know it's lean. So pull it back. It always pulls too far. Air fuel ratio sensors can't tell exact ratios. They can just tell it's rich or it's lean. If you got a 0.9, it's not really substantial. It just means it's rich. If you got a 0.1 or 2, it doesn't really mean it's very lean. It just means it's lean. It's not really very proportional. Make sense? So they're fine. But if you're really trying to hit the 14.7 tight, clean on the money, not going to cut it. So here's what a wideband O2 or an air fuel ratio sensor can do. Right here, it's rich, right? How rich? It's rich, like rather than 14.7 to 1, it's 13.2 to 1. What should we do? Move it to 14.7. That's it. It's not like, whoa, too far, too far, too far, too far, right? With O2 sensors, it's always overshooting. With an air fuel ratio sensor, if you look at it, it stays still. It stays still because it measures exactly how rich it was or exactly how lean it was. It just corrects it. So if you pull a vacuum hose on that, you'll really quickly see it go lean, but then a lot of times it'll pull it back to center and correct it. It'll do that through fuel trim, which is what we're going to talk about next. Okay, so an O2 sensor might be $30. A wideband or a AF is going to be $300.
You gotta order them.
They're probably not going to want to stock them. They're pricey. Yeah, I'm not that shocked. And the other thing is, it's one of those things where, again, it's hard to test it, right? So if you put an O2 sensor that's cheap or an AF sensor that's cheap, it's not. And how do you diagnose it? Like, it's one of those things where it's hard. You can't exactly get an air fuel ratio from the sensor and like hook it up to the dyno with the calibration gas that you accidentally happen to have at your place. The smog ref could do some of that, but it's one of the things where if you do put a cheap one in, it's hard to diagnose. MAFs are kind of the same. Temperature sensors, not so much. You put a cheap temperature sensor in and you think it's an issue, just compare it to the actual reading. You're like, oh, this is no good. But once you're into these sensors, they're hard to really verify. So I would shy away from doing a real cheap O2 or AF. I would also shy away from doing a cheap MAF. Yeah, still struggling with it. All right, new word for you is lambda. So when we talk about air fuel ratio, we're talking about 14.7. Lambda is another term for that. A perfect lambda would be 1.0. So if you pull up the scan tool and it says bank one, sensor one, air fuel ratio sensor, lambda 1.0, that means it's 14.7 exactly. I actually can't recall which way lambda goes because I'm usually thinking fuel trim, but sometimes they use.
It goes down,
Okay, so 0.9 would be rich.
more like 0.85 would be like 12.5 or something.
Okay, I believe you. That's the type of stuff you'd remember where you got a fake hatchet stuck in your head. See, what I see is disturbing right now. But actually, I believe you. So if it's running rich, your lambda number would go down. Maybe you get 0.85. We'll go with that. So if your vehicle's running rich, your lambda won't be 1.0. It'll be like 0.85. If your vehicle's running lean, your lambda won't be 1.0. It'll be like maybe 1.15 or something, right? So your lambda number tells you if it's rich or lean, if it's equipped with the lambda live data PID parameter ID. Sometimes you just have to look at the AF, and the AF will either say like positive or negative, right? They're a little bit, they vary a little bit from one manufacturer to the next. Cool. All right. And so when we look at the wideband, it's very similar to O2 to me. They don't look any different. They just cost a lot more, and they can actually give you an exact reading of your air fuel ratio. Look, they operate 1292 to 1472 degrees. It's pretty gnarly. So these have O2 heaters, and they're strong heaters, and they need to get really hot before they can read, and they want to get them hot really fast. And they use this nursed cell right here. And if you want to go all into the details of the oxygen pump and the diffusion gap, you could totally geek out on how this works, but ultimately it's going to move oxygen into the cell or out of the cell to have a balance. And if it has to move oxygen into the cell, to have a balance, that means the cell itself is lean, and it has to move oxygen out to match that's how it determines that it's rich, right? So it's literally got a mechanism to make the oxygen move out or in and make it match. Kind of weird. Cool. All right, that was inputs. All right, everybody good on inputs? Inputs are all those sensors. Now let's talk about processing. I added something late last night to this that I've never had before, just for you. And it was late. So with processing, it's hard to see, it's hard to understand, it's off limits, you're not allowed to touch it, like you just know it's in there, right? Because modifying this is going to be modifying your emission standards. So why do we need to know? We need to process a lot of information to get the correct air fuel ratio, to get the correct ignition timing, etc. For example, we need to know engine speed, fuel pressure, transmission temperature, what the driver inputs are, so like the accelerator pedal or the brake pedal, or etc. Engine temperature, both oil and coolant, right? So, and all these previous inputs that we have, we need to know all that information. But why do we need to know it? I guess I shouldn't say we. Why does the ECM need to know that? That's exactly it. If you had an old school carbureted car, you go ahead, you fire the car up, and the amount of air that's going to go in the carburetor is going to depend on your cam and your headers and your intake and your air filter and your K&N and all the fun stuff, right? And then you're going to have jets in the carburetor that are going to be about this big. And if you have this much airflow, you have this big of a jet, that jet should provide approximately 14.7-ish. We're probably going to run a little rich, maybe a little 13, maybe a little 12.5, maybe a little 12 parts of air to 1 part of fuel. That'd be rich. That's like, some people might call it fat. They'll run better, more power and all that type of stuff. But you ain't going to pass smog around here. I'm just letting you know. In other states, no problem. All right. In other countries, put coal in the thing and burn it till it billows black out the tailpipe. And that's just fine in some of these other areas. But here, no, you can't do that. All right. So let's just say you went in, you're like, you threw headers on it. Now it's got even more airflow, right? How would you get the gas to make up for the additional airflow? Tune it is current. Carburetor, you'd have to go in and take the jet out and get a bigger jet and put a bigger jet in there, right? Even dirt bikes and stuff, we were doing that stuff up until like 2011. So like even some of my stuff, I put a cam and an exhaust in or whatever, and I'd do some research and be like, oh, I'm going to bump the jet up from a 180 to a 185 main to make up for the additional airflow I just got. And the bike's, if you punched it, and you saw like a puff of black smoke, you'd be like, oh, you know what, it's a little too rich. And then you put a smaller jet in there. And then if it wasn't really making max power, you might put a little bit of a bigger jet in there. You're experimenting, right? You take the jet out, you put a jet in. That's how carburetor stuff were. It was approximate. And anytime you made a change, you had to physically change the jet. But then when you went up to Big Bear, it was not going to run that good. There's no adaptation for elevation. There's no sensor, there's no computer, there's no nothing. It was just, you could get it tuned good here. Even true for my bike today. I got a couple of bikes that are still carbureted. Not the one I ride right now, but my dirt bikes are carbureted, and I get it running so good, and I'd be like super happy with it. And then I do some crazy ride, and we'd end up in Idlewild or something, and I'd be like, this bike's popping and stumbling, it runs like crap. And I'm like, did I get bad gas? And then I come all the way back down the hill and it runs perfect again. Old school, there's no adjustment for any of that type of stuff. I actually put a bunch of adjustable jets on mine so I can adjust mine as I'm riding, because I get kind of like, not really OCD, but like, because I understand what's happening, I'm frustrated when my air fuel ratio is off because my elevation changed. Same with temperature. When you have really cold air, it's more dense, right? When you have warm air, it's less dense. So if it's cold air, you need more fuel because there's more oxygen in the set amount of airflow. Cool. So all those adaptations, carburetors don't have it. ECM, we need all those inputs so that we can fine tune how much fuel we spray out of the injectors. And we can adjust the timing, and we can adjust the idle speed, and we can adjust all this type of stuff. And that's why if you jump in a modern vehicle, you start it up, it starts good, it idles good, it has good power down here, good power at Big Bear, good power at the Huntington Beach at 3 foot of elevation, right? It just runs good everywhere. That's because it has all these inputs that are constantly fine tuning and tweaking and changing, right? That's really why we need all those inputs. Cool. So the ECM takes those inputs, it looks at its programming. For example, this is my late edition. This is a program, HP Tuners. This is not legal for smog requirements. This is how you go in and you could adjust some things. So I could go in and, for example, now I would not do this, but let's say I've got a vehicle that has O2 sensors. And okay, I'll make this a lot more legal real quick. How about that? That'd be better. I take an LS. This is a 5.3 liter LS, and I put it in a 65 Mustang just because. Ha ha ha. Roll over in your grave, Henry. You just got LS swapped in your Mustang. Or something, whatever. Put it GM to GM just to keep it GM. I put it in some old Chevelle. How about that? I put it in a Chevelle. I don't necessarily want to run rear O2 sensors in a Chevelle because a 60, gosh, I don't know. If it's a 60, let's say it's a 72 Chevelle, they might have. Yeah, they had a few different things at that point, but it's a 72 Chevelle. There's no emissions requirements on that. So am I going to put cats on it? I don't think so. If I don't put cats on it, I don't want rear O2 sensors. I'm not even going to put them on there. If I put that LS in there and it doesn't have rear O2 sensors, you know what it's going to set? HO2S heater control circuit bank 2 sensor 2, P0056. I can turn that off. I can say, no longer set the code. I will literally change the monitor. I'll go over here and don't enable the service engine soon. Turn the mill to just no error reported. I can literally make it no longer set DTCs. Cool. So that's really legit when you want to do cool swaps and custom things. Where to get your butt in trouble is when you can't fix the car and you've tried the sensor and you tried a bunch of stuff. And you're like, you know what? I'm just going to go in to this 2016 Silverado and make it think that it doesn't have cats and no O2 sensors anymore and just force the check engine light to not come on. That's when you've modified emissions. Make sense? If it's older than a 70, I think it's 76 and newer. If it's 76 and up, you can't change that stuff. That's done. However it came from the factory is how we're supposed to keep it in California. If it's older than that, yeah, you can turn all this stuff off. Absolutely. Like, for example, if you put a really aggressive cam in there, it's so lopey, it'll a lot of times set a misfire code, and you can't fix it because it's not a misfire. It's just a really aggressive cam. You could go in and look up a P0300 and turn it off. Just turn it off, right? This is how the ECM actually works. The ECM is got programmed logic, right? So I would go in here and I would change its logic to say, when you see these things, don't give me a check engine light. Or I'll give you another example. This, for example, is idle speed. Remember I had the customer who had the issue on the car and they said like it tickled or whatever. It was just a little tickle. All right. I could go in there and be like, I don't want 725 anymore. Actually, this is mine. I'm going to admit it. This is my Hummer. With the cam and all this type of stuff, if I left the idle at what it was, which is like 650, it would be like just about to die. Like if you put a big cam in some, it won't idle well anymore. So I had to bump my idle up to 725. But when it's cold, like if it's 25 degrees, so I found out when it got cold like a couple winters ago, it was running good, but then I went out to start it in a cold morning. It wouldn't even run. It would just not run. So I had to bump that up to 1100 RPM. And then when it hits 46 degrees, I could drop it to 800 at 68, 800. Once it's up to 90, I'm just going to lock in 725 idle RPM. So you can see from left to right is coolant temp. And then these are the speeds. I just typed those in the box. I upload the file and now the vehicle idles at whatever RPM I told it to. You see what I'm saying? That's how the ECM works, but the ECM needs to be programmed to take an action. If my coolant temperature is 111 degrees, the ECM is programmed to increase my throttle motor to make the engine idle at 725, right? So I just wrote logic right here and made it do it. That's what the ECM really does, okay? This all happened in a different state, so you know. So nobody's going to tell me nothing. Or, for example, when we talk about timing, we talk about ignition timing. If you notice, this started off green, which is kind of cool. Green is not a lot of timing. But as I have the RPM go up, I have it go more and more advanced. That's why it starts to look warmer and warmer and warmer. At, let's say, 4,200 RPM, I'm doing like a 45 degrees of positive ignition advance. That's a lot. It didn't come with that from the factory. You know what I picked up? Mm-hmm. Yep. And it runs a lot stronger. It's a lot more spicy, But how did I do it? I went in the ECM and I rewrote it. So there was some stuff over here like 4 degrees. And I'm like, nah, we're going to add this. But then this is the thing. When I'm rewriting the tune, I'm going like, I'm off of the known path, right? So for regular text, we don't rewrite the tunes. The engineer writes the tune. But just so you understand, though, the purpose of the ECM is to look at information. For example, 2,200 RPMs as indicated by the crankshaft position sensor. And the left is your air mass in grams. If you're at 2,200 RPMs and 0.48 grams, we're going to get 20 degrees of ignition timing, right? That's what the ECM does. It looks at these logic tables and then it says ignition timing, 22 degrees, or whatever it is, depending on RPM and air mass. Cool. And there's tables on tables on tables on tables in there. There's tons of tables. The one that you won't commonly see is the air fuel ratio, because that's one where like you pretty much want 14.7 on that. But there's a thing called open loop, which is coming up. If you went into open loop mode, that's when you'd kind of want to run a little rich, because that's when you're like wide open throttle. You can adjust that. I didn't really show you on here. So you can literally write in, you want it to run 14.7, or you maybe want it to run 13, a little richer. You maybe want 12.5. It's going to have good power. You're going to probably have excessive hydrocarbons. You're going to probably fail smog. Okay. But just talking about what the ECM does, an engineer wrote all these numbers in here, uploaded it to the ECM. That's the logic in the computer. You can't, unless you buy this, you can't change it. And if you buy this, you're breaking the law. You're breaking the law if it has emission standards. And then the manufacturer sent the vehicle out to be tested by the EPA, and the EPA tests it as is, and they certify it, and it's approved. So the manufacturer doesn't take lightly change these numbers and redo this type of stuff, because they already had it approved by the government. You don't get it approved and then change it. Then you're supposed to get it reapproved. They got to pay a lot of money to have the government test their emissions. So you know. All right. And then let's just say that was a little bit of tuning, okay, unofficially. This is more like from the factory. Remember we talked about how sometimes the ECM can have a bad calibration that'll cause a problem, like the lady with the tickly seat. The idle was just too low. Like the idle was just too low. It's not something that we can really change. Well, it's something that the engineers could make a new file and it would correct the issue. And then they might send out a notice and say like, hey, bring the car in. Then you'd log into your service info and it'd say, hey, there's a fix for this low idle and the tickly thing and the whatever. Upload this file into there, boom, and it'll fix it. And you don't always know exactly what they've adjusted in these, but it's very common for technicians to do ECU updates. They may call it a reflash. If you hear the term reflash, that just means you pulled the old software programming out and you put in some new stuff, has a new number, it's going to fix some things. It's really the same as when your phone does an update. It's just the same as when your apps update and all your stuff updates. Most of the time, we, the technicians, have to do this. Sometimes they can do it over the air on some of the new cars. They'll just do an update, like your phone. You'll come out and you'll be like, hey, there's an update. It says it fixed something. Back in the day, we would have to do it. And then there's some regulations, specific connectors and stuff we have to use. You're going to use the scan tool if you're doing it. We're connected with the scan tool, connected to the computer. You have to have the scan tool on the internet. You usually have to have some sort of a username and password to log into, let's say, for me, the Toyota system, or back in the day, it was the Kia or the GM system, or sometimes the Honda system. And you can get the file, but you got to get the file from the manufacturer with your username. So if you're working at the independent shop, you're not going to have the file. You're not going to have access to the file. You also will need the scan tool and then this little green box. I'll show you. That's similar to this. So these are all programming boxes. They'll go from USB to OBD2 connector, and that's actually a programming interface. Cool. When you go to do it, right here, there'll be like a calibration ID number. So you might find a TSB and it'll be like, do you have this calibration ID number? If you have this one, you should update it to that one. Makes sense? So that's what we're showing here, the calibration ID. Now, when I was showing you some of this, like some of the things I told you I changed, when I make changes, it changes the calibration ID. So when I go to get smogged, California's like, this isn't the ID that it came with. That's how they'll bust you. You understand? The good news for me, my truck is so rare. I don't think they knew the calibration IDs. So I don't think they know what mine was supposed to be. Plus, mine's been tuned for many years. So when they were gathering the calibration IDs, they're probably like, oh, here's a calibration ID. Like, haha, gotcha, suckers. So my stuff is legit. But if you were to take something that was like pretty common, like a Mustang, there's a lot of Mustangs. If you start changing this stuff, you change the calibration ID, they're going to flag that. Right? These are the approved ones from the manufacturer. When you do your own stuff, you get your own and you got to fly. HP Tuners actually has a good way to copy the original one though and make it look like it's legit, but well, I didn't say anything. All right, outputs. Here we are. So you got the inputs, you got the processing. Now you understand. Like Mason, for example, has got good calibration in there. When you throw at him, he's like, I know what to do. If for some reason I threw that thing at Mason and he was like, it'd be like, Mason, we got to recalibrate your brain. Next time you see a marker flying at you, yeah, it might be a problem in the, maybe it's a problem in the processing. Or maybe we're getting into the outputs. Maybe he has a problem with the bicep and he couldn't lift his hand to block it. I don't know, right? So when we have a problem with the car, it could be a problem in the processing, but that's less likely. More likely, it's a problem on the inputs. Maybe Mason was blind. Or maybe Mason saw it, but he just didn't have good control of his bicep, right? So sometimes problems are on the input side, the sensor side. Sometimes problems are on the output side, the actuator, the motor, the whatever it is, with a rare occasion that it's actually in the processing. All right, so here we go. So here's some outputs. Fuel injector on time. What do you think that means?
It's not late.
Yeah, close. This is how long it stays on. I got you. That was a joke. I went over my head at first. No, it was funny. It was fun. I thought you meant that you thought we were timing the injectors. I realized what it said. Fuel injector on time. It's not running late. Gotcha. All right. The fuel injector on time is how long it's on, how long it's off. All right. So if we were to go wide open throttle and the air was cold and the map said that we're making boost and the mass airflow said we're moving a ton of air, what do you think I would do with my injector on time? Increase it, right? If I turn it on longer, fuel sprays. Injectors go on, off, on, off. If I've got a whole bunch of inputs saying, hey, we got a lot more air coming in, the ECM is going to say, injector, increase on time. Blast it with fuel. Cool. That's injector on time. That's an output. An output's like an action. Injectors don't sense, they don't get information, they do work. They spray fuel. That's their job. That's why it's an output. Kind of makes sense? Injector is an output. Ignition is an output, right? The ignition sparks the spark plug. It sparks it early. Like my original timing was like 4 degrees. My timing after the tune is like 45 degrees, right? So I wrote the logic to make the action different, but ultimately the output was still the coil. The coil's the output. Okay, cool. Idle speed. So like, for example, if it's cold outside, we want a higher idle. The ECM will command the throttle to open a little bit more. That'll give us a higher idle. Or in an older car, it was an idle air control valve. The idle air control valve would open a little bit, and that would increase the idle, right? But those are outputs. The idle air control motor does work. It doesn't sense. Cool. Transmission shifting, when it's just variable valve timing, displacement on demand, there's all sorts of other outputs. This is just a small example. Cool. Sometimes the output's simple as turn it on or off. Other times it's more complicated, like it'll control on and off time, like duty cycle, or PWM is pulse width modulation. If we pulse width modulate a fuel pump, that means we turn it on and off and on and off. So that way it's not on all the time. Remember the old pumps we just used, we'd run them full speed all the time and they didn't last that long. Now we're like, turn on, turn off, take a break, turn on again, turn off, take a break. Okay, we're going up a hill, turn on, you don't get a break right now. All right, we're at the stoplight, take a longer break, right? That's pulse width modulation, right? And then there's a thing called multiplex. All right, there you go. Multiplex is computers talking to computers. All right, so how about this? We go to start the car. We want to know what the ambient air temperature is. Don't you think when you go to start it, the computer might like to know what the temperature is outside? The PCM doesn't know the temperature outside. You know who knows that? The HVAC ECU. The air conditioning ECU knows the outside temperature. So if we have one ambient temperature sensor, we'll let one ambient temperature sensor send a signal to one module. Then we'll have that module send a message out on this whole CAN network and be like, hi, for anyone who cares, the outside temperature is 71 degrees. And the ECM's like, oh, yeah, I care about that. And now the ECM has the information. But the sensor was wired into the HVAC ECU. The sensor is not even wired to the ECM, but it got it on the network. You see what I'm saying? So that's this term called multiplex. If the engine ECU wanted to know the transmission fluid temperature, it would probably wait to hear from the transmission control module, hey, what's the ATF temp? And the transition control module is like, yeah, we just started. It just hit 81. And then the engine's like, thank you, right? But if you think about it, if you have one sensor and you can have it go to one module and then those modules can communicate, saving a lot of wiring. Imagine if you had 5 computers that all wanted to know your ambient air temperature. You're gonna have 5 ambient air temperature sensors or 5 harnesses going to all these different places. It's nuts. So once they started doing more multiplex, it makes a lot more sense, right? So simply put, multiplex is all these modules down on the bottom, all of them, right? It was too big of a thing to really be able to see it, but this one's a fuel pump control module, accessory drive, accessory power, engine control module, transmission control module, right? All these different modules are all in communication with one another. The reason why that's on an output is if you have the engine control module and it wants to tell the transmission control module to shift sooner, that's an output, right? The ECM is going to say, hey, TCM, shift sooner. And the TCM is going to be like, oh, I heard you. All right, got it. Boom. See how that's an output? Technically, inputs are multiplexed as well, right? Any input to any computer can be multiplexed, and any output from any computer can be multiplexed. Cool thing. All right, first real output is a relay. How do you think the ECM can control this relay? You remember? Like here's your diagram. We've got a relay on here. We've got several things on here, but if we look at this big relay right here, let's just say we have 12 volts coming in on 30. And if we want to power the pump, we need to send that 12 volts to 87 out. Do you know how we would switch it from 87A, which is off, to 87, which is on? Okay, so how would we do electromagnetic here? Maybe 85 gets voltage all the time, so we could have the ECU provide what to 86? Bingo. So if we have the ECM simply give a ground or not give a ground, that'll control a relay. ECM is going to say, turn the fuel pump on. Oh, how's it do it? It grounds 86. That's it. ECM just grounds 86. We got bigger power, bigger fuse power going to 30, and then 87 is what carries it over to the pump, right? So a relay is an output. A relay does work. A relay electromagnetizes, closes the switch, and turns on the pump or the whatever it is. Cool. And so if you were to try to test it, we just do basic relay tests. So the coil, we could do an amp test. Effectively, if the ECM provides the ground, you'll see an increase in amps, and that's going to actually magnetize the coil and pull the switch over, right? So that's it. ECM's just turning it on or off by giving it ground. Here's another output, solenoid. Anybody know what a solenoid is? I'll give you my most common example.
A coil, copper coil, making a magnetic wave.
You're pretty much there. I mean, you're there. All right, let's say that we had that copper coil going around a little rod. And if you give the rod 12 volts in ground, it goes dunk. And if you give ground and 12 volts, it goes dunk. 12 volts in ground, dunk. Ground and 12 volts, dunk, dunk. Does anything look like this when you were a kid in the back seat playing around? Dunk, 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 dunk. Yeah, exactly. So I like to picture solenoids like the power door locks. If you send 12 volts in ground, it'll magnetize it and it'll move whatever is inside of it. To move it one way, negative to positive, to move positive and negative, move it the other way. Solenoids do stuff. Like, for example, maybe this is a transmission solenoid, and a transmission solenoid will make a transmission shift up. If it doesn't get 12 volts in ground, it doesn't shift up. But when it does get 12 volts in ground, it opens, it sends fluid to the next clutch pack, and it engages, boom, and then you're in second or whatever. The more common one for us in engine performance, injectors. Injectors are solenoids. If you had fuel pressure go into this, and the only way to get it to flow was to move this inward, you could magnetize it, positive and negative. It would pull it over, and then fuel will spray.
That's how you check fuel, you jump it, right?
You can do it like that. That's one way. There's a few ways, but that's one way.
That too, right?
There's quite a few different ways. Yep. Right. So that's a solenoid. And we'll talk a little bit about injectors in a bit, but solenoid is a common output. Remember, when the PCM wants to control it, here's a lot of times how it'll do it. It'll be providing ground or maybe voltage. So like in this case, we flipped over to ignition. And when we're going to do our ignition control, do you see these symbols right here? You guys from electrical remember what that is? A little hard to see. They're kind of like switches, right? If I had a switch right here, this could give ground pulses to this coil. Give ground, give ground, give ground. But remember the ECM, it's not real good at mechanical switches. It's better at electronic devices, such as a transistor. Bingo. So the transistor, if we give a little ground on the base right here, it'll send, or if we give a little positive on the base, it'll send ground to this coil and make it fire, right? So you're going to see over and over again, we're going to use a lot of transistors.
What's a transistor? Is it something that changes?
It connects or it doesn't connect. So if you picture a relay, right? A relay is open unless it gets 12 volts in ground and then it closes. Essentially, a transistor is like a solid state relay. There's no moving parts. It's semiconductors. It's trying to send, like in this case, actually, you know what? This is actually sending voltage. It's sending 12 volts to here, but 12 volts doesn't go through and to the coil unless it gets the right signal in this middle part, which could be a ground. So if this gives ground, 12 volts will make it to the coil. If this does not give ground, 12 volts will not make it to the coil. So they'll call it like a driver sometime. So the ECM is just simply giving ground, not giving ground, giving ground, not giving ground. And that's going to control the transistor, which is going to power the coil, or it's going to fire the injector, or it's going to do something, right? So that's how the ECM is controlling the output. It uses transistors inside. You think there's any possibility that that transistor could fail?
Yes.
And if it did, how would we fix it? Hilarious. Never seen it done. Somebody might. What's the technician going to do? Replace the whole ECM. But you better make sure that you're right. Because if you're telling me you think it's got a bad transistor, a bad driver inside the ECM, I'm going to say, why? And you'd be like, well, I checked for voltage on 3 and it didn't have it. And then I'll be like, look, did you check for voltage on 30? You're like, yeah, and it didn't have it. And I'll be like, did you check 11? Yeah, that one was pulsing. Well, that's kind of weird. Yeah. If 30 is not pulsing, it could be that transistor. Sometimes I'll be like, clear the codes. Just make sure that that ECM is not purposely not firing that coil by clearing codes and stuff. And then if it's, if all the codes are cleared and it's still not giving voltage on terminal 30, you would diagnose that as a bad driver, AKA transistor in the ECM. Okay, it is what it is. All right, cool. Another output is an IAC motor. So motors are outputs. Idle air control is just how it sets the idle. So if you start the vehicle and you're hoping, based on all the inputs, you want an idle speed of 1200 RPMs because it's kind of cold and whatnot. What it'll do, it'll send 12 volts and ground to the idle air control motor, and that will initiate this to move clockwise. See that? And it'll move clockwise until it opens up enough to allow enough airflow to hit 1200. Once it hits 1200, it'll take away the 12 volts in ground and the idle air control motor will stop. Okay, makes sense? Then let's say that it wants it down to 800. It'll do not 12 volts in ground, but ground and 12 volts, which will turn it counterclockwise, which will lower it back down until it sees 800, and then it'll tell it to stop, right? So the ECM is commanding this motor to move one way or the other to get the correct idle, which is a little old school. Now, more likely, we're going to use this throttle actuator motor. This is drive-by-wire electronic throttle. So this connector right here is the throttle motor and the two TPSs. Remember that, the two throttle position sensors? So what it'll do, let's say you want, let's say the ECM gets the APP, remember the APP, and it says 50%. And the PCM is like, yeah, 50% sounds legit. My programming approves. It sends a signal to the actual throttle actuator to move the motor to 50%. How does it know to stop sending 12 volts in ground at the right moment? Can you think about that? Remember what's in here too? The two sensors? So it's, remember, if it's a TPS, let's just say it's going from 0.5 to 4.5 and from 4.5 to 0.5, right? There's opposing TPS sensors. It'll run that motor until it goes to 2.5 and 2.5, right? So it'll run the motor until it sees the correct voltage on the two sensors to confirm it's in the right location. Make sense? The sensors are inputs though. The actual motor is the output. Okay, cool. But it's kind of interesting. All right, so that's actually a good example of the full loop. APP says 50. ECM's like, cool, I'll go with 50. It got the input. It processed the input with the logic. Then the output is send that throttle motor to 50%. That's the input, the process, and now the output. The output was move it to 50. Then what's interesting is it goes right back to input because it's a loop, and it's going to say, are you at 50 yet? And the TPS is like, no, I'm at 48. I'm at 49. I'm almost there. Chill. Keep running it. I'm at 50. And then the ECM sees 50%. And then the output is throttle motor, stop moving. You're perfect. Then, of course, you know, got one of you in the driver's seat and you're like this with the gas pedal, burp, 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 burp. And the throttle motor's like, rah, 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 like overworking. But that's the input, the process, and the output. Kind of makes sense. Input was the sensor, process was the ECM, output was the motor, which then looks at another input, which processes the input, which outputs to tell the motor to stop, and around and around and around and around. Cool. And then again, we talk about the limp-in fail-safe. So if you had any error in that electronic throttle thing, if there's any disagreement, if there's any lack of if there's any disagreement between the two sensors, or if there's any disagreement between what it commanded and what it actually has, boom, fail-safe, limp-in mode. Cool. All right. A small preview on fuel trim. When we're talking about the input, process, output, a bunch of sensors are going to be inputs. All right. And that one of them is going to be the oxygen sensors. Those oxygen sensors give numbers, and then the ECM processes, and then it's going to make an output. So if we look at a whole bunch of air fuel, if we look at MAF and MAP and all this stuff, and we say, okay, as a result, I think I should do the injector on time 25%. That might be right, but then at the end of the day, the O2 sensors see what the result is in the tailpipe, and then it's going to say, no, you were off a little bit. You're running a little bit too rich. You need to lean out a little bit. If it wants you to lean out, that's going to be a negative number. If it wants you to richen up, that's going to be a positive number. Okay, so that's kind of a preview because we're linking that to input, process, output. But fuel trim tends to be something people struggle with, so we're going to cover it one more time. Cool. All right, and then just keep in mind, the engine communicates with a lot of other systems. So that could be vehicle theft deterrent, entertainment, stability, HVAC. That's all that big multiplex thing. It's a lot of stuff going on.
So those things on an on the ECU,
Connectors
they have a.
or the fins.
They have a safety.
Yeah, connector
flags,
position
right?
assurance. Yes, because we don't want them.
Because I was looking at it for my daughter startup on it.
Uh-huh.
I was looking at my,
Yeah, this is actually a Chrysler. So you see that red one? All the Dodges be having that.
Yeah.
You got to pop that down to the left and then push another thing. When you go to disconnect these, they can be, you gotta look carefully and take your time.
I took off my, the map.
Yeah.
And I just went in and looked at it. Cleaned it and
Yeah.
put it back, see,
Yeah.
like that.
I just thought of something, like, so like with the gas plugging stuff thing. the
Sure.
5 out wire,
Mm-hmm.
what if you, you're driving, and while you're on the gas, the throttle connector, suddenly just unplugs, would the ECU be able to close the throttle body?
Yes, it's good question. The throttle is sprung. So if you don't have 12 volts in ground, it automatically closes. You need to run the motor against the spring and it draws power to actually hold it open. Pretty good idea. Yep. Yep. Okay. And then again, when the PCM is referencing inputs, for example, an analog or a digital, these are going to provide speed or position, et cetera. So the ECM is looking at all of these and going to process that as information. And then when we talked about the programming, there's a term we're going to use here, EEPROM. So that's electronically erasable programmable read-only memory. It's located in PCM. It's similar to a hard drive that retains all the learned features, can't be replaced, no moving parts. Everything I told you about the tune, that's more like the base programming. But then after that, the vehicle does some level of adaptation. So when we start talking about EEPROM, it could be for like idle RPM, right? If you start your car and you want an idle of 700 RPM, that's great from day one. It should have no adaptations required. It should be ready to go. But what happens as you drive it 100,000 miles and there's carbon buildup on some things? Now the carbon buildup is blocking some of the airflow from the throttle. Now your idle is too low. What do you think the fix is? If you bring it in the shop, the technician cleaning it would fix it, but they want the vehicles to be more reliable, so they allow it to do adaptation. So it might have to open your throttle a little extra to compensate for the carbon. Can you visualize that? It will adapt over time. So if you, let's just say, for example, you disconnect the battery on a car and you reconnect it and it has a hard time idling, sometimes it's going to take time to relearn that idle RPM. Sometimes it's going to take time to relearn the transmission shift points, the fuel trim strategies. Like if you clear codes, a lot of times this stuff is reset. And you actually might find it idles weird and shifts weird until you drive it for a bit. So this is some level of adaptation. Does that make sense? Because we're going to continue into how the vehicle adapts. There's quite a bit of adaptation in there. Cool. All right, so you do a throttle body service. You know what that means? You pull the intake off and you clean the carbon out of the throttle body. You start it up and the idle's too high. What do? You could reset it, or you could drive it. A lot of times driving it can take a long time though. So I would reset it and I'd let it idle and maybe drive it a little bit until it feels good. And then I ship it. And you'd be like, what did I do? Well, you could say you did nothing, but what you really did is you gave it the time to do the adaptation and now it's normal. If you ship it to the customer's gonna be like, this thing doesn't idle right, you messed it up. When you try to tell the customer, well, it's got to relearn. And they're like, what the heck you mean learn? Like car doesn't learn. It kind of does actually. So you'll get those base programming numbers and then it can tweak it a little up or a little down as part of the EEPROM adaptations. Okay, cool. And then we talked about those drivers a little bit. I thought you might like to see them a little closer. So 12 volts comes down, 12 volts will not go through to the coil unless we provide a ground, right? So when we talk about ECM drivers, just remember, it's a whole series of transistors that control stuff. The drivers control the outputs. Make sense? And then part of the reason that we like to do that is like, you know, if we have a component, maybe it's the fuel pump, we could eliminate the driver and just have the ECM just turn it on and that's it. But if we can pulse it, give it some off time, maybe increase its life expectancy because it's not running all the time. We can also vary the fuel pressure, decrease the electrical consumption, right? There's good reasons why the ECM is why most manufacturers are going more to like duty cycle or pulse width. We're not having things powered all the time. We're going to turn on and off as needed. The ECM is really good at that, using those driver, like that driver, like all this. There's just going to be countless drivers for things. So ECM does a lot. And then the calibration, I think you should be pretty good. When we looked at those HP tuners things, that's all operating. That's all changing how the drivers are controlled. Make sense? It's going to say to the driver, turn on more or turn off more, something like that. Okay, now here we go. This is fuel trim, just fuel trim now. Okay, this might hurt you, but we're going to do our best. Go ahead. Okay. All right. Fuel trim, it's still input, process, output, okay? But I find fuel trim to be one of the harder to understand. So we're going to get down and dirty on it. Let's first, to understand, you got to know open and closed loop. Do you see right here? Is this loop closed? It's open. It's not looping all the way, right? What that means is the output is not monitored. So when we try to close the loop, that means we want to monitor if the output was right. So like on a basic example, when we talked about that electronic throttle, the APP said 50%. The ECM said, yeah, command 50% on the throttle actuator motor. If that stops and that's it, it's open. Do we know if it worked or not? We don't have any verification, right? We want 50, we told it 50, did it give us 50? I don't know. The loop is open. So how would we close the loop? We would close the loop by adding a throttle position sensor. The throttle position sensor would verify that the throttle motor moved to 50%, right? And then it would take that information and it would send it back to the ECM, which could do fine-tune adjustments, which could control an output, which will initiate a mechanical change, which could be monitored down here. When we close the loop, closed loop means we have like the full monitoring of the situation. This is going to say, I want 50%. Hey, they want 50%, give 50%. Okay, this is actually going to move to 50%. This is going to monitor that it did in fact move to 50%. And then it's going to, again, fine tune it. And it's just going to make sure it's what it's supposed to be. That's the example of a closed loop. Now, when we say closed loop, we're typically talking specifically about the fuel system. So here is open loop. You got a bunch of sensor inputs, right? Think of all those sensors: mass airflow, map sensor, engine coolant, intake air. O2 sensor, almost, not yet. The O2 sensor comes in when we close the loop. If we're open, the O2 sensor is not counted yet. When you first start the car, you know why we're in open loop? O2 sensor won't work till 600 degrees. And if it's an AF, more like 1300. So we start the car, we're in open loop. What that means is all the sensors, correct. All the sensors are telling the ECM their information. The ECM's like, based on my programming, I think I should do this, this, and this injector on time. But is it good? But is it giving us 14.7? I don't know, because the loop is open. Make sense? The O2 sensor is not relevant yet. You can't look at it. It's too cold still. That's why. So when you first start the car, it's an open loop, right? And then after a while, like when the heated O2 sensors are warmed up because they run the heaters, then it should go to closed loop, okay? This loop is now closed. We've got the sensor inputs. They're the same. We already had those. They give signal to the ECM. We're going to say spray more or spray less fuel, just like before. But when we spray more or less fuel on the injector, we're now going to look at the exhaust, and the O2 sensor is going to say how good we did or how bad we did. And if we sprayed too much fuel, that's rich, right? Too much fuel is rich. So the O2 sensor is going to say, hey, my voltage is high. You're rich. And you know what it's going to do? It's going to give feedback to the ECM, and the ECM is going to trim it. That's what fuel trim is. It's fine tuning the fuel trim. It's adaptation. Make sense? Because who's to say? Maybe you have injectors that are a little dirty, a little clogged, right? What do you think would happen? What do you think would happen if your injectors were a little clogged? Would they spray more or less fuel? Right? So if they sprayed less, what would your air fuel ratio be? Less fuel is lean, yeah. Less fuel is like more air, which is lean. So your O2 sensor is like, hello, 0.2 volts, you're lean. Trim it the other way. Add a little bit of injector on time to compensate for your dirty injectors. You get what I'm saying? So if you jumped in the scan tool, you could actually look at the fuel trim numbers. If your fuel trim numbers are 0, you know everything's functioning great. If your injectors are kind of dirty, it's going to start to pull your fuel trim numbers high. If you have a vacuum leak or an unmetered air leak, remember that? I told you you're going to come back to that. If you had an unmetered air leak, you have extra air making it in. What's that going to make the engine run? Rich or lean? Lean. So what do we need to do to the injectors to compensate? Increase them. You're right. If there's extra air coming in, we need to increase the fuel to match it. Because at the end of the day, we need that 14.7 in the exhaust to pass our emissions and stuff. All right, to be legit. So what fuel trim is, it's a number that's a percentage of how much we're having to add or subtract to get 14.7. Okay, cool. So you got all these inputs, and then you got the ECM like, yeah, I know what that means. I should do 50% duty cycle on my injectors. And then you got the O2 sensor saying like, nah, 50% isn't going to cut it. Trim it up 5%. And then the ECM's like, okay, cool. I'll fine tune it 55%. And then the O2 sensor's like, that's right there. Hold it right there at 5% trimmed up fuel to make up for that air, unmetered air, or the dirty injector, or your sort of clogged fuel filter, or your whatever. Now, what do you think is going to happen as that fuel filter continues to clog up worse and worse and worse? Before that happens, though, all that's going to really happen is the O2 sensor is going to say, hey, you're lean again, trim it up to 10%. Hey, you're even lean again, trim it up to 20%. Once you start to get above 20, 25, like 25 especially, all of a sudden you're going to get a code, fuel trim lean. And you're like, what? Remember we talked way back in the day, you bring your car to O'Reilly's and they give you a code P0171, fuel trim lean. You're like, what part do I replace? And they're like, okay, I just described you fuel trim lean. If your fuel trim is lean, that's because it's already thrown 25% extra fuel at it and it's still not there. Then you need to really diagnose, why is it lean? And you got to look at all the things that'll make it lean. Dirty injectors, restricted fuel pump, unmetered air leaks and vacuum leaks, right? So it's like, I don't know, which one is it? But that's not all. What if you had one of these sensor inputs that was a little off? What if your mass airflow sensor was showing less air when it was really more air? That would make it run lean, right? You'd have too much air and not enough fuel. So we might actually have to like look at a lot of our inputs, look at a lot of our sensors, try to determine why are we trimming the fuel so much positive? That's fuel trim lean. Okay, cool. What if we had an air filter, a K&N, and it was really clogged and dirty? Would that restrict airflow? So is that rich or lean? Lean is too much air. Rich is not enough air or too much fuel. I agree. So if you had a restricted air filter, you don't have enough air, but in the meantime, these still think you kind of have a good amount of air. So it says, yeah, spray 50%. And then the O2 sensor is like, dude, 50% is way too much. Trim that back 20%. If it's a negative 20, that means the engine is lean and it's pulling 20% fuel. It's negative 20% trimmed.
See all this in that.
Oh, yeah. Oh, yeah. When you want to look at it, here you go. I'm going to come back to that one just so you know. Look at this right here. Your short-term fuel trim is 3%. That means we're trimming it positive 3.9. That's not bad. 3.9 is good. Look at our short term on bank 2. We're trimming it positive 6.2. That means we're spraying 3.9 on bank 1 extra and 6.2 on bank 2 extra. So it's running just a little lean, but that's not a bad number. Look at the number 2 example. 20% on short term on bank number 1. 20%, that's a lot. You're adding 20% of injector on time to make it run 14.7. Something's wrong. And look at your bank 2. Now I'm focused on short term. Short term is instantaneous. Short term is like, what do I need to do right now to get it to read 14.7? If you have short term running 20% for a long time, that will start to leave short term and go into long term, right? So if you had a car, it was 0-0, and you disconnect the vacuum hose, it may very well run 20% positive, but that would be short term instantaneous. But if you were to leave it running with no vacuum line for like the next week, this 20 would decrease to probably closer to 0. And you'd end up moving all that 20 down here to long term because it's doing it every day. So your short term tells you right now, and your long term tells you over the course of the previous weeks and months. All right, makes sense? But when you take your short term and your long term, here's your actual calculation. When you're looking at your injector duration, you're gonna look at your MAF and your RPM. Then you're gonna look at your long-term fuel trim. Your long-term fuel trim, remember, that was written over time. So if you got an injector or like a fuel filter that's clogging up, it's gonna slowly but surely show up as short term, which will slowly but surely be written as long term. Your long term's a big factor. Then it's gonna look at some minor sensor corrections and your short-term fuel trim. And it's going to calculate for your battery voltage change, right? Because if you have a high battery voltage, that's going to change how your injectors open and close. It's going to compensate for all these things.
I mean, every time you want to turn it on.
It's running all the time. 24/7, all these are being adjusted to fine-tune, perfect that air-fuel ratio. That's why these fuel injected cars, they just run clean. They start good, they run good. It's like, that's why our emissions are so low on a modern vehicle. We're running nearly 14.7 all the time, perfect. Even if you had a little bit of a clogged fuel filter, we'll see that on fuel trim. That fuel trim will write it into long-term fuel trim, and it'll just correct it. It's pretty wild. Yeah. Boom. Yep. Yeah, the fuel injections, nice. Yeah, exactly. No, they're really legit. Now, when you go to diagnose fuel trim, this gets to be a little bit more difficult. So like a short-term fuel trim right here, I'm looking at this and I would say this is fairly minor. I would overall consider this normal. So if you see numbers and they're single digits, I'm not worried about it. Especially when there's basically nothing on long term, that's good. Now, if you look at this one's short term is 20 and long term is 19. So those are going to be combined when they set the injector duration. That thing's spraying like an extra 40. There's something severely wrong. If I were to look at this, I might be able to figure this out. Like your MAF reading 4.39, that might be legit. Your coolant temperature sensor at 183, that kind of makes sense. Although, you know what? Here's what's interesting. We had, that's a little tough to say.
Air leak? Vacuum leak?
Good chance. I would probably say, because one thing I can notice is we're only at 859 RPM. We're probably like just barely off of idle. Vacuum leaks are very prevalent when you're near idle, but for me to really diagnose this, I'd want to rev this up. If I rev it up and the fuel trim goes more normal, I would say vacuum leak. Yes. But if I rev it up and the fuel trim gets even worse, I would say maybe it's starving for fuel. Right. So I'll show you that in one more screen. FYI, if you want to, as an output, you can control the injection volume. You could manually add fuel to it and just see if the O2 sensors and the air fuel ratio sensors respond appropriately. Now, if I was looking at diagnosing the fuel trim like this, here's what I would do. Let's say we look at these. This is normal, right? Normal should be about 0. You agree with me? That'd be good. What if we had that unmetered air leak or a vacuum leak? Your fuel trim would be really positive at idle, but then as you got towards wide open throttle, it would be normal. Why do you think? Why do you think? It's a good idea. Not that. Think of it, when your throttle's closed, you make a lot of vacuum and you have very little air coming in. So if you have very little air making it past the throttle plate, but then you have like extra air sneaking in an unmetered air leak, that's going to be like a big difference, right? It's almost like this. Remember the pizza and soda deal? Let's say you got pizza and soda deal and you only got a few people coming in, but then you got some people sneaking in the back window. That's going to have a big impact because you don't have that many people coming in anyway. And you still have people come in this way and be like, oh no, we're way out of balance. But then what if the doors blow wide open and there's tons of people rushing in and you still have a few people coming in the back door? You're not really going to notice that much because you're collecting so much money, right? So when you're at idle, the vacuum leak is a major problem. But when you're at wide open, it's sort of like you're sucking in a ton of air anyway. What's a little bit extra? That's why it went from really bad to at wide open throttle, it went to like almost normal. That's what a vacuum or unmetered air leak looks like. Cool. You want to see what a mass airflow sensor that's dirty looks like? A MAF, because the MAF doesn't have to measure that much air at idle. It might be a little bit off, but it's not measuring that much. So it's off by a little bit. You can't tell. When you go under wide open throttle, the MAF should read a lot of air. But if your MAF is not reading well, it'll get worse and worse and worse. This MAF, yeah, this MAF right here is like wearing a blanket. This has contamination on the hot wire. If it's wrapped up in hot wire and all of a sudden there's a lot of air going through and it's wrapped up in a blanket, it's going to be like really not seeing all the air. When there's a little bit of air, it's not seeing the air, but there's not that much air. But when there's a ton of air, it's like, I don't think there's that much air. It's going to be further and further off 0. So you see this one's getting to like 15, 16% at wide open, but at idle, it was near 0%. It was almost normal at idle. It gets worse as you go. That's a MAF. That's kind of opposite of an unmetered air leak. An unmetered air leak is really bad at idle, but almost normal under wide open. See, so when you go to O'Reilly's and they don't know what part to sell you, you'd be like, well, it's a fuel trim lean. Let me look at the fuel trim numbers. If the fuel trim number is bad at idle and it gets kind of normal when you rev it, I'd be like, this is an unmetered air leak or a vacuum leak. If the number is pretty good at idle and then you rev it and it gets really positive at wide open, I'd maybe suspect a MAF. And we didn't necessarily measure any voltages. We're just looking on the scan tool and revving it. And then here's an example of a restricted fuel. It's very similar to the dirty MAF, but it's going to get worse and worse and worse and worse. This one almost lets off a little. Think about the fuel. When do you need the most fuel? At idle or wide open?
Wide open, high revs.
All right, so if you're high revs, wide open throttle, and your fuel trim's getting more and more positive, that's telling you those injectors are trying to spray up to 30% more and they still can't keep up. Maybe they don't have enough fuel pressure pressurizing the fuel rail because your fuel pump's worn, your fuel filter's clogged, right? So this one's even more extreme case of it gets worse as you rev it more. Cool. It's fuel starvation is what it is, right? And then how about if we got an AF that's biased? Well, they can fail in either way, but they don't fail more or less under load or at higher or lower RPMs. If it's an air fuel ratio or an air fuel or a O2 sensor, it's just going to fail. Like it's going to be showing too positive or too negative just all the time. You're going to rev it, no change. You rev it up, no change. You let it idle, no change. You're just going to be like, the fuel trim is just off on this. That would be more of an indication of a AF or O2 sensor. All right, pretty cool. Kind of intense though, huh? Did you think you got it? Because fuel trim's all over A8 though. And so you process this and think about it. Plus I'll give you the recording. And then when we get to do the lab, we'll do some fuel trim stuff, right? So the good news is you guys made it. We are there. It was intense and you made it.